Greetings and welcome, friends. Me and my amigos in geometry class. As we hang out, we were doing some Geometer's Sketchpad, and we just discovered some wonderful properties of triangles and some special segments, of which we will have, I believe, 5 special segments that we talk about in triangles in this chapter. And we are talking about 2 of them today. So first, some terminology. Because words are effective in describing things, we should have words to describe them. It says, when 3 or more lines, rays, or segments intersect at the same point. Notice it says 3 or more, right? So instead of like an intersection between 2 lines, gentlemen, please. If I have 3 or more intersecting, it's called a point of concurrency, right? And those are concurrent lines, rays, or segments. In a triangle, check this out, if I draw the 3 perpendicular bisectors, it turns out they are concurrent, and that the point of concurrency is called the circumcenter of the triangle. And here's a little property about the circumcenter. It says that it is equidistant from the vertices of the triangle. To prove that to you, check this out now. Funk's your brother. What's this? Oh, la 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 la. It is equidistant because I just drew a circle, and all 3 of these segments are radii, and therefore they are congruent to one another. So the circumcenter is equidistant from the vertices. It's also the center of the circle that you could draw that would pass through all 3 vertices of a triangle. Amazing. So let's solve a real-life problem, friends. All right. Ooh, here we are. Look at this. It says 3 snack carts sell froyo from points A, B, and C outside a city. Each of the 3 carts is the same distance from the froyo distributor. Find the location of the distributor. So, let's do this. It's going to exist at the circumcenter, and I can find the circumcenter. So you guys will need your little compass tools here. By constructing perpendicular bisectors, so I just pick a radius that's more than halfway between 2 of my sides, like so. And if I draw that line through those 2 points, so I'm perpendicularly bisecting AB is what I'm doing here. And I think I'm getting better at it, guys. It's true. You've got to admit it's getting better. It's getting better all the time. Let's do another perpendicular bisector. I'll change my radius just so it's not as obviously the same thing. So I draw 2 arcs such that, oh no! Okay, that's fine. They still intersect. I was worried I didn't give myself enough of a point there. So I draw 2 arcs from each endpoint of the segment such that they intersect using both of their intersections, because there's going to be 2. Those intersections form a perpendicular bisector like so. All right, so even though I've only drawn 2 perpendicular bisectors, this is going to be the point of concurrency. But let's draw the 3rd one for the amazing reveal that it is, in fact. All right, let's prove me wrong then. Let's find out. So let's draw the 3rd perpendicular bisector. Let's see, I'll go there a little bit. All right, and so these are arbitrary radii, as long as they're longer than the midpoint of the segment AC here. Let's see, it looks like it's gonna done intersect here. Oh boy, let's see if I get some concurrency. Da-da-da-da! That's amazing, guys. It's amazing. All right, but this is where my froyo, what is this? A distributor is. And let's actually see, because this is the concern, gentlemen. Is this point actually equidistant from abaca? How could I show that? I could measure it, but if I use my compass tool, make it center there, and then I swing through. Actually, this froyo distributor is run by the Illuminati in an underground basement bunker So you don't need roads where they're going. They have underground tunnels that allow them to transport froyo to all of their distributors so that they can control the public. So yeah, so these three red segments, yeah, I just overdrew it there, would be congruent because all three of those are radii of the circumscribed, right, triangle circle thing there. Bam. Look at that. That thing's amazing. Also, I don't know, my students were talking about Illuminati, so that's what I'm doing. I gotta relate to the kiddos these days. You gotta stay relevant, you know? Gotta stay Relev. That's what they say on the streets. So let's see. We also, in manipulating our geometer sketchpad sketch, came to the conclusion that acute triangles have a circumcenter in the interior. Obtuse triangles will have a circumcenter in the exterior. And a right triangle will have a circumcenter that is directly on the hypotenuse. And it actually passes through the intersection between this perpendicular bisector and the hypotenuse. Therefore, it's actually the midpoint of the hypotenuse. Amazing reveal. Blah, 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 blah. Right, wow, you guys are in shock. All right, let's take a look at example 2. All right, here we are. So, interlude. Find the coordinates of the circumcenter of triangle ABC with vertices as given. And I conveniently pre-graphed these for us and then equipped you with said graph. I believe I did, right? You guys got it in your packets? You're good. All right. So let's find these perpendicular bisectors. The easiest way would be to look at the ones between A and C. Now, if these points were not so conveniently placed on the grid, you could construct perpendicular bisectors just like we did last chapter by finding the midpoint, finding the slope of a line, finding the perpendicular slope of a line to that one, and then finding the equation of that line, and eventually finding the intersection between two of those equations. Yeah, exactly. Maybe we'll end up doing one of those Tamari. We'll see. But if I want to find the perpendicular bisector of AC, this midpoint I can find rather easily by taking those coordinates. It's just going to be the difference of their y coordinates absolute valued. So 3 minus a negative 1 is 4, and yeah, divide by 2 is going to be halfway. I could use the midpoint formula. If I add them up, divide by 2, 3 plus negative 1 is 2, and divide by 2 is 1. So here's my midpoint. And if I want to construct a perpendicular bisector, that's a vertical line, which has undefined slope. What's the slope of a line that is perpendicular to that? What the slope of AC is undefined. It's a vertical line. What's the slope of a perpendicular line to a vertical line? Yeah, so it's horizontal and has a slope of 0. Let's find the perpendicular bisector of BC. All right, here we go. So if I want to find the midpoint of BC, it's horizontal. I could just find the average of the x-coordinates between B and C. Add 0 and 6 together is 6, and divide by 2, I get 3. And its y-coordinate is going to be at the negative 1. So over 3, down 1. Here's the midpoint. BC is a horizontal line. It has a slope of 0. A perpendicular line to a horizontal line is going to be vertical and have an undefined slope and is going to look like that. And the concurrence, the point of concurrency between these happens to be right here, which is also the midpoint of the hypotenuse. Alternative strategy would have been to recognize these were right. This was a right triangle, and that then I could have just found the midpoint of that. And midpoint formula, by the way, works just fine for all of these. Midpoint formula, of course, is the average of the x's, add them up, divide by 2, and the average of the y's, add them up, divide by 2. Man, this one has almost got like... Man, I'm never going to be able to do that again. But nonetheless, let's see. Let me show you guys a little Desmos. Here's this problem in Desmos. If I want to see the solution, I can construct these perpendicular bisectors. And let's see, this one's not going to work. That's sad. That perpendicular bisector, yes, sorry, is going to be the equation x equals 3, like so. And then I could change the color there if I wanted. All right, and then if I want to find that intersection, I could just click on this. It looks like the solution, wait a minute, 0.5? Wow. Yeah. It looks like the intersection is occurring at, right there. Yeah, that's 3, a half. That done be it. So there you can see that does in fact work out. All right, so let's take a look at, let's see, I do have other examples in there that you can give a try, but for sake of time, let's talk about our next special segment and their point of concurrency. So a triangle, just as a triangle has 3 perpendicular bisectors, it also has 3 angle bisectors that happen to be concurrent. The point of concurrency is called the incenter. It is always going to be on the inside of the triangle, unlike our circumcenter that we had in the previous case, where for obtuse triangles, it could be on the outside, or for right triangles, it was on the edge. For any triangle, the incenter always lies inside the triangle. I just said that, man. Great job, Mr. Waddy. Here's the incenter theorem, the IT. The incenter of a triangle is equidistant from the sides of the triangle. So, this little sketch over here, these are angle bisectors. What's up? Oh, you're stretching? All right. Because all this math leading is fatiguing our bodies. We gotta do our stretches. So these blue segments in my sketch are all angle bisectors. There's a point of concurrency at P called the incenter, and they are saying it is equidistant from the sides. That means, right, because we measure distance perpendicular to a line, that's why these are labeled as perpendicular, and that means that these are all equidistant. And since they're equidistant, that means if I was to draw a circle like so, it would be the perfect circle that would barely intersect each side exactly once. Which actually, have we talked about that concept? That it's possible to draw a line that passes through a circle at exactly one point? I don't think we've ever talked about that. Have you known that to be possible? Yeah, I guess like imagine balancing like a piece of plywood on a basketball. Like you could imagine it's touching that ball at exactly one point. This is said to be tangent. So this line is tangent to the circle. You can have tangent lines to curves as well when they intersect at exactly one point. And so so this circle is said to be inscribed in the triangle and has a center at the incenter. All right, and so that's kind of a cool little property right there. Let's do an example. Let me see if I can screenshot this all in one go. There we go. Example 3. Guys, isn't this just like magical that these special segments all happen to be concurrent and then have cool properties? You guys have never known this about triangles before. It's amazing. Oh man, what? Everyone cares about triangles. Triangles can change your life. All right, find NF. All right, in the figure shown, ND is equal to 5x minus 1. NE is equal to 2x plus 11. And they want us to find the length of NF. These 3 blue segments are all labeled as angle bisectors. Therefore, this incenter is going to be equidistant from the sides, and all of these smaller segments are congruent to one another. If they're congruent, then by def of Kong, their measures are equal. Therefore, what you thought of long ago is true. 5x minus 1 is equal to 2x plus 11z's. Yeah. Actually, question, if you were a Pokemon trainer, would you consider them athletes? Is Pokemon battling a sport? No? Okay. The student's answer is no. I don't know. You have to have a bond with your Pokemon, you know? Hmm. That's physical. Yeah. So guys, NF is equal to NE, which is equal to 2x plus 11. I plugged it in. Let's see. The question is, can NG equal to 18? Explain your reasoning. So guys, here they're asking about NG. Wow. Guys, check this out. My sports leets. Could this distance be 18? If this distance is 19, and it's perpendicular to this distance could not be shorter than it. That is not perpendicular to it. The shortest distance from a point to a line is perpendicular, and this number could not be less than 19. It could not be equal to 19. It would have to be greater than 19 in order for that to work out. So the answer is no, because it is not the shortest distance to the segment AC, and therefore cannot be less than 19. Wow, interesting. Little bit of trivia there for us. Okay, here we go. Mr. Tumnus is gonna like this problem. This one's for all you Narnians out there, all my fans hanging out. I guess they don't think they're in a wardrobe. It's just you could think they're kind of like in a wardrobe from our perspective, but as far as they know, the wardrobe's just a doorway to Narnia. It's not like Narnia's contained inside of it. But let's see, City wants to place a lamppost for Mr. Tumnus on the boulevard shown so that the lamppost is the same distance from all three streets. Should the location of the lamppost be at the circumcenter or incenter of the triangular boulevard? So they want to find point here so that it's the same distance from the streets. What type of point am I looking for? No? Anybody? Let's see, well, circumcenter would be... Yeah, circumcenter would be equidistant from these, but they wanted equidistant from the street, so that's going to be a point that would be perpendicularly measured to those, but is found by constructing angle bisectors. Let's construct some angle bisectors here real quick if I can. Let's see, I'm bad at this. I might only have time for two. All right, so I'm going to draw an arc, and then to bisect an angle, I'm going to shrink this down, but at least past the midpoint, and from that point, and that looks way too similar. I don't want to confuse us. There we go. There, and then the same distance there. Here is an angle bisector. You guys getting good at constructing? Are you feeling it, Mr. Krabs? We actually have 3 points to go off of here. All right, let me construct one more here. I'll use orange this time. So I'll bisect an obtuse angle. That sounds dangerous. Okay, there we go. I'm going to go past the midpoint here a little bit. Like that. and then over to this side. Oh, wait a minute. Where did I just do that from? I don't know if I went by the yellow line. I'm supposed to go by this one. There we go. All right, all right. I was worried for a moment there. Okay, here we go, here we go. Still got time. I've got to place this lamppost for Mr. Tumnus. Okay. The claim is that this point, yeah, we've got time. Don't pack up. Sit down, gentlemen. Is that this point is equidistant from our edges. Is it? That's arguing that I could draw... Guys, go back to your seats. Get out. You're in my way now. Literally. Go back to your seats. Sit down. Sit down. What is this? That I could now draw a circle that is equidistant from all three. Oh dear, it looks like I failed. Guys, did I fail? I might have gotten a little too sloppy. There you go. Well, thanks for watching, internet friends. Have a great day.